Section 8.4, de Moivre's theorem, powers and roots of complex numbers. Let's first talk about de Moivre's theorem. De Moivre's theorem gives us the ability of raising complex numbers to a power and computing that value quickly. For example, let's say we had some complex number in polar form, r cis theta, and we want to square that. Well, squaring a number is the same as multiplying it times itself. So this would be r cis theta times r cis theta. And using what we learned in the last section, when we're going to multiply, using our product rule, when we multiply two complex numbers in polar form, we just simply multiply the r values together. So that'd be r squared. And we add the angle measures together. Theta plus theta would be 2 theta. So this would be r squared cis 2 theta. So we'll start seeing a pattern. If this was a 3, let's say we're going to cube this. Well, this would be r times r times r, or r cubed. Theta plus theta plus theta would be 3 theta. So to generalize, r cis theta to the nth power would be r to the nth power cis theta plus itself n times would be n theta. So here's what we have, what's called de Moivre's theorem. Complex number in polar form to raise to a power n, simply raise r to the nth power and take n times the angle measure. So what does this allow us to do? Well, given a problem like let's find 1 plus I root 3 to the 8th power, we don't want to sit here and use the FOIL method over and over and over again, multiplying this times itself, take that product times itself again, take that product times itself again, do that 8 times. De Moivre's theorem gives us the ability of computing this relatively quickly. So we'll start by taking the polar number 1 plus I root 3, that's currently in rectangular form. Let's convert it to polar form and raise it to the 8th power. 1 plus I root 3 is the same as 2 cis 60 degrees. And let's raise that to the 8th power. Now we can use de Moivre's theorem. Well, this is simply 2 to the 8th power cis 60 times 8 would be 480 degrees. 2 to the 8th power is 256. So we have 256 cis. Now let's find the coterminal angle with 480 degrees, and that's the same as a 120 degree angle. So now we have 255 cis 120. Convert that back to rectangular form using what you've learned in section 8.2, and that would be negative 128 plus 128 I root 3. So you can see it's much quicker to use de Moivre's theorem than to stay with rectangular form and multiply it over and over and over and over again. So since de Moivre's theorem allows us to raise complex numbers to a power, we can also in a sense go in the opposite direction and find roots of complex numbers. So let's take a look at a theorem, roots of complex numbers. Every non-zero complex number has exactly n distinct complex nth roots. What we mean by that is every complex number has 2 distinct square roots. Every complex number has 3 distinct cube roots, 4 distinct fourth roots, etc., etc., etc. N distinct nth roots. So what exactly is an nth root? For a positive integer n, the complex number a plus bi is an nth root of the complex number x plus yi if we can take the first one, raise it to some power, and get the second one. For example, 2 is a square root of 4. Why? Because 2 to some power, 2 gives me 4. Nth root theorem. If n is any positive integer, r is any positive real number, and theta is in degrees, then the non-zero complex number, r cis theta, has exactly n distinct nth roots given by the following formula. We'll simply take the nth root of r And then there's a somewhat of a complicated formula to come up with our different angle measures. So for k equals 0, 1, 2, etc., however many that we need, this is our method for coming up with those angle measures. So if we're looking for the two distinct square roots, we're going to use k value of 0 and 1. If we're looking for the three distinct cube roots, we'll let k be 0, 1, and 2, three of them. Let's go over an example. Find the three distinct complex roots of 8 cosine 135 plus I sine 135, or how I'm going to think of it is 8 cis 135. So we're being asked to find the three complex roots of this complex number. So somewhere out there, I know there must be three numbers, three complex numbers in the form of r cis theta, such when I cube them, right, cube roots, such that when I cube them, I will get 8 cis 135. See, finding the cube root of 8 cis 135 is the same thing as saying, well, let's find the three values that I would cube. We had a theorem earlier saying that since I'm dealing with cube roots, I know there are three distinct answers. So find the values such that if I cube them, I get 8 cis 135. Well, now there's where de Moivre's theorem kicks in on the left-hand side. R cis theta cubed would be r cubed cis 3 theta, and that must equal 8 cis 135. So what's this imply? It implies that r cubed must be the same thing as 8. And if r cubed is equal to 8, taking the cube root of both sides, we know that our r value is equal to 2. That's the easy part. Now we need to come up with our angle measures. So I know that our angle measures will equal 135 plus 360k divided by n, which in our case n is 3. And we're going to do this formula for k equals, since we're looking for cube roots, we're going to let k go from 0. We're going to also use a value k value of 1 and also k value of 2. Here's how we'll come up with our three distinct cube roots. So what are our theta values? Well, let's let k be 0. 360 times 0 is 0, and 135 divided by 3 is 45. Our next theta value, theta sub 2, let's let k be 1. 135 plus 360 divided by 3 is 165. And our last theta value, theta sub 3, let k be 2. 135 plus 360 times 2 divided by 3 is 285. So what's the overall answer to the problem? Well, we found our three distinct cube roots. Using this r value and using these three angle measures, we have the answers 2 cis 45, 2 cis 165, and 2 cis 285.